Just a sec. Okay, welcome everyone, and we are very happy to have the second lecture of Shu-Heng.
Okay, thank you, Slava. All right, so okay, so today I'll continue the lecture. So yesterday we talked about some general definition and aspects of anomalies, and then we went over a few examples of anomalies in quantum mechanics. And then we talk a little bit about the 1+1D free boson, but we haven't got to the anomaly part of the 1+1D free boson. So in the lecture today, we will mainly focus on the 1+1D free boson. I will start with some review of what we discussed yesterday. So the free boson Lagrangian is just the standard one. There's an important coefficient out from. It's usually called the radius of the compact free boson. It's an exactly marginal deformation. So it gives rise to a family of conformal field theory with C equals to 1. Importantly, phi is a compact field, and I'm using the normalization that it has 2π periodicity. Alternatively, you can rescale your R into your definition of phi, and then the periodicity of phi will depend on R. There are two interesting global symmetries, which will be important for the rest of the lecture. So let me just go over them again. There's a manifest U1 momentum symmetry. The adjective momentum comes from the string theory terminology. What it does is to shift the phi by a constant. The Noether current is just given by this, and the Noether conservation equation is the equation of motion. There's a more subtle symmetry, the winding symmetry, whose currents are given again by derivative of phi, but you exchange space and time. And you see that the conservation equation is trivial. And then yesterday we discussed a little bit more about the winding symmetry. The momentum symmetry acts in a very easy way, shift phi. But the winding symmetry, what does it act on? We did identify a winding configuration. It's a classical field configuration, which gives rise to a quantum mechanical state carrying non-trivial winding charge. But it's still mysterious what the winding symmetry acts on. And then we talk about T-duality. T-duality is a rewriting, is an exact rewriting of the original compact free boson with radius R into another Lagrangian using a different field, a dual scalar field phi tilde, but now the radius is 1 over R. The manipulation is completely standard. At each step, we integrate in some field and then integrate out some other fields. Every step is completely rigorous, and it's all at the quadratic level. And that duality transformation take you from radius R to 1 over R, meaning that the compact free boson at radius R is the same CFT as the compact free boson at radius 1 over R. These are just two different presentations of the same underlying CFT. You can show that the original field phi and the dual field phi tilde are related as follows. So roughly speaking, the time component of the field phi is now mapped to the spatial, the time derivative of the original field phi is now the spatial derivative of the dual field, and vice versa. And therefore, it exchanges the momentum and the winding symmetry. That's what T-duality does. And from this point of view, it's then clear that the U1 momentum symmetry, it shifts phi, which was our fundamental field. And the U1 winding symmetry simply shifts the dual field phi tilde. So that answers what the winding symmetry acts on. So that's what we discussed yesterday. Is there any question at this point? Okay, if not, let me continue. So now let's talk a little bit about the spectrum of this C equals to 1 CFT. Note that I haven't gone to the anomaly yet. I just introduced the Lagrangian, I talk about the T-duality, and I talk about the two U1 global symmetries. And then let's talk about the spectrum of local operators. So at any radius r, there's a lowercase u1 times u1 Kac-Moody current algebra. I use lowercase because, well, Kac-Moody algebra is generally defined with respect to a Lie algebra rather than a group. And more importantly, as we will see later on, if you pick a generic radius, there's generally no left-moving capital U1. We will come back to this point later. But since I'm just talking about local operator spectrum, we can still organize them using the left-moving lowercase u1 Kac-Moody and the lowercase u1 right-moving Kac-Moody current algebra. So the primary operators with respect to this u1 cross u1 current algebras are denoted as follows. It's labeled by two integer charges. Little n is the integer charge of the U1 momentum symmetry. Integer W is the integer charge of the U1 winding symmetry. And it can be simply written as this. Right, so U1 momentum shift phi, and if the operator involves e to the in phi, it obviously carries the charge n. I should make one comment though, that this O and W, they are well-defined local operators in this C equals to 1 CFT, but the field phi itself is not really a good local operator. Among other things, phi is identified with phi plus 2 pi. So you can think about the 2 pi periodicity as some kind of integer gauge symmetry. So phi is not really a gauge invariant local operator. Rather, exponentiation of phi is a good operator. So the full spectrum of the C equals to 1 CFT are given by these operators, as well as the identity, which you can view it as the n equals to W equals to 0 case. All right. Now, there's one piece of information that I will not derive in the lecture, but it's well known in all the textbooks, which is to compute the conformal weight of this U1 current algebra primary operator as a function of your momentum charge and the winding charge. So I leave it as a homework, and the answer is given as follows. So the left moving conformal weight is given by this, the right moving is given by that. And just to relate these two quantities to the scaling dimension and the spin, let me just write it down. So this delta is the scaling dimension, it's the eigenvalue under the dilation. This S is the Lorentz spin. So delta and S are related to H and H bar by this linear combination. Okay, perhaps the most important formula that we will need below is this one. The Lorentz spin of the local operator is given by the product of the momentum and the winding charge. Note that the momentum and the winding charge, they are both integers. So the Lorentz spins are also integers. Of course, that has to be the case because we are talking about a bosonic CFT at this point. By definition, every local operator in a bosonic CFT have integer Lorentz spins. That's why how they can be mutually local with respect to each other. From this formula of the conformal weight, you can also see that as you perform the T-duality, you take R to 1 over R. And the spectrum of local primary operators remain invariant if you exchange your momentum and the winding charge. That confirms the previous statement that, that the T-duality exchanges momentum and winding with winding. Okay, now we can talk about the two-hoof anomaly of this 1+1D free boson CFT. There's a mixed two-hoof anomaly between the U1 momentum and U1 winding global symmetry of this continuum field theory. The adjective mix means the following. Okay, one way to think about this two-hoof anomaly is to view the group simply as U1 cross U1. Actually, let me write it in a more illuminating form. You can think about the group as U1 cross U1, and then there's a two-hoof anomaly for this group, U1 cross U1. Another way to look at this in this particular case is that it can be viewed as a mixed two-hoof anomaly between two global symmetries, meaning that if you turn on the background fields for this guy, then the partition function will not be invariant under this gauge transformation. And vice versa, if you turn on the background gauge field for the winding, then the partition function will not be invariant under the momentum gauge transformation. So let's try to see that more explicitly. I think this is arguably the simplest anomaly among low quantum system, even though it's in 1+1D, many of its aspects are easier compared to the quantum mechanics counterpart. Among other things, the symmetries are all U1s, and we are all familiar with how to deal with U1 background gauge fields and U1 gauge transformation. So let's do that. So let's couple the free boson CFT, and importantly, to background classical gauge fields. So these are just some fixed value in your partition function. We are not integrating over these two gauge fields. So the blue A mu is the background fields for the U1 momentum symmetry. The tilde A mu, the red tilde A mu is the background gauge field for the U1 winding symmetry. Let's first focus on the blue gauge field. How do we couple that? Well, that's easy. We know the U1 momentum symmetry shift phi. So all we have to do is to make the derivative of phi a covariant derivative. A covariant derivative is not precise because the symmetry is realized non-linearly. So what you really do is to shift the derivative of phi by A mu. Okay, so this part is easy. How do we couple to the winding symmetry? Well, there's a general rule on how to do that. If I have a current J mu, and I want to couple it to, let me erase the tilde. If I want to couple it to background gauge field, I simply contract its index with the gauge field A mu. What was the current for our winding symmetry? Well, let's go back a few slides, is this. So all I have to do is to contract this guy with my red winding background gauge field. And that's exactly what I wrote here. So you can see that this part is the current for my winding symmetry. And I just contracted with the background gauge field for the winding symmetry. I will be in Euclidean signature, and I'll assume the spacetime is flat, so I will not be too careful about the upper and lower spacetime indices. All right, so we are almost done, but as I mentioned in the previous lecture, we always have the freedom to add additional term of our background gauge field. So our background gauge fields are A and A tilde. And I can just add more terms involving them into my action. Here, I'm going to make a particular choice just to simplify my life slightly. I'm going to add a term that takes the form of A tilde wedge with A. And that's the final term here. Let me just mark that. And the reason to add, the motivation for adding such a term is that I want to make this derivative of phi also covariant. But of course, I can add other terms. It's completely up to me. But let me just make this choice for convenience at this point. All right, so this is my way of coupling the free boson CFT to the U1 cross U1 background gauge field. Now we are ready to check the gauge transformation. The gauge transformation of the U1 momentum symmetry, note that this is a background gauge transformation. So capital A is held as a fixed background value, and now I'm changing it by a background gauge transformation. So the background gauge transformation shift phi by alpha and shift A mu, by the usual gauge transformation. And A tilde is also transformed under the U1 tilde, the winding gauge transformation, and the gauge parameter is denoted as alpha tilde. If there were phi tilde in my action, then I also have to shift phi tilde. But I choose a duality friend where phi tilde doesn't make an appearance. So I will not write the transformation of phi tilde. Okay, so let's do this gauge transformation. The first term is obviously invariant under the U1 cross U1 gauge transformation. So we don't get anything from this term. This term is also, this piece is also gauge invariant. The interesting part is that when we do the gauge transformation of A tilde, we have two terms. So let me write it down. Okay. This piece is a total derivative, so I don't have to worry about it. And therefore, what I'm left with is, note the normalization is important, so let me keep track of it. Okay. And finally, I'm going to integrate by part to move the derivative acting on A, and I end up with this expression. Is everything clear at this point? I think this is one of the simplest calculations to show that there is a mixed anomaly. So what have we learned? We learned that this is nothing but the field strength of the U1 momentum background gauge field. So what we have learned is that if we have a non-trivial background gauge field configuration for the momentum symmetry, then the winding gauge transformation is no longer invariant. So this signals the mixed anomaly between the two. And you can convince yourself that no 1 plus 1D local counterturn of A and A tilde can cancel this anomalous gauge transformation.
Question?
Yeah, go ahead.
So about this, about adding other counter terms, is it correct that if I choose another coefficient for the blue A nu, the local piece you added, I can make this anomaly go around between the two U1s, right?
That's correct.
Be proportional to, and it's alpha tilde times F plus alpha times F tilde.
Yeah, you can shift the anomaly. You can add local counterturn to move the anomaly around. Yes.
Okay, thanks.
And here I made a choice. Okay, so let me just repeat one of the earlier slides. So, and I think this is a very nice and concrete, easy example of the general discussion we had yesterday. So yesterday we said that, oh, if I have a quantum system T with some global symmetry A, here A actually will collectively stand for the blue U1 and the red U1. I have this partition function and I perform a gauge transformation on the background gauge field, I obtain an anomalous phase. This anomalous phase cannot be canceled by the 1 plus 1D local counterturn, but there's a 2 plus 1D invertible field theory that can cancel it. Well, let's try to understand that 2 plus 1D invertible field theory in this particular case. In this particular case, well, this is supposed to be blue. Like that. In this particular case, we see that the anomalous gauge transformation is given by this. It's the gauge parameter of the winding U1 times the field strength of the momentum U1. How do we cancel this by a 3D or 2 plus 1D counter term? Well, here's an easy candidate. You pick a 3 manifold whose boundary is the 2-dimensional space-time of our free boson, and you extend your gauge field to the bulk. And then you see that the gauge variation of this guy manifestly give you this. Right? Because if I do the gauge transformation, A tilde goes to the A tilde plus the alpha tilde. And then even though it's a total derivative term, this manifold Y3 has a boundary, and we pick up this boundary term. And you can think of this term as the 2 plus 1D invertible field theory, or in the condensed matter language, the 2 plus 1D SPT with symmetry U1 times U1 for this anomaly. Okay, and later on we will constantly use the 2 plus 1D or the invertible field theory to characterize or track our anomaly. In fact, in practice, that's also how people classify anomalies in various contexts. In many cases, instead of working with the 1 plus 1 dimensional manifold, they go to 1 dimension higher and try to classify consistent invertible field theories. Okay. All right, so that's the anomaly of the 1 plus 1D free boson, and that will be the then player driving the show. Now I want to make another comment, which is about the global symmetries in free boson CFT. At any radius r, we have talked about a momentum U1 and a winding U1. But usually we also hear people saying that there's a left moving U1 and a right moving U1. And I think it's useful to figure out the relation between them. So first of all, at any radius, these two U1s are the fundamental U1s. What do I mean by fundamental? I meant any other U1 global symmetry is an integer linear combination of the momentum U1 and the winding U1. So by knowing this two, you don't miss anything else. If you know the other U1s, you might not get everything. But if you only have access to this two, then you are good. You can generate all the other U1s this way. Okay. Now, so any other U1 is the integer linear combination of the two. And a general integer combination, let me call it the purple U1, will have a 't-Hooft anomaly by itself. And is captured by this Chern-Simons SPT. So now this A is the background gauge field for the purple U1, and the coefficient is slightly modified. What's the relation with the holomorphic or left-moving U1? Well, before we discuss that, let's define the holomorphic and anti-holomorphic coordinates in Euclidean signature. Then it's an easy exercise, and which I actually find quite illuminating to do, is to determine for what value of the radius do we have a holomorphic U1 current. And what do I mean by holomorphic U1? I meant the following. You take the momentum U1 and the winding U1, you pick two integers n and m tilde, and you consider this following linear combination. That's the most general U1 you can consider in the free boson CFT. And you get a current. It has a vector index. By a holomorphic U1, I meant such a current whose z-bar component vanishes. So it's a very simple linear algebra problem you can do. You just have to take the definition of J mu and J tilde mu, plug this in, and go to the holomorphic coordinates and check whether it's possible to have a holomorphic U1. The answer is that It's not always the case. And you only have a holomorphic there is a holomorphic U1 if and only if the radius square is a rational number. You can roughly see that because what you are going to do is to take some linear combination of this piece with that piece. And you want certain components of it to vanish with some integer coefficients. But one of them comes with coefficient r squared, the other comes with coefficients 1. So the only chance there can be a cancellation is when r squared is a rational number. So at the generic radius, there's actually no holomorphic capital U1 symmetry. You still have a holomorphic current. You just take the holomorphic derivative of the field, but that globally generates a R symmetry rather than capital U1.
Can you be a bit more specific about this R symmetry? What do you mean by that?
I just meant that if you take this current and you construct its charge, so you can write it as this. And then you put a group element theta there. Well, maybe I shouldn't use theta. So let me write something different. X, no, X is a terrible name, R. So then you have this operator, U R, acting on your Hilbert space. But there's no periodicity of R. So that's why globally it's not a U1. For U1 symmetry, you expect that theta plus 2 pi is the same operator as U theta.
But otherwise, would it be a good symmetry?
Otherwise, a good symmetry. Yeah, no problem with that. Still conserve. It's just a global form.
Okay.
Okay. So at any radius, we have the U1 cross U1 current algebra. But notice that I used the lowercase. When R squared is rational, from this formula, you can see that two primaries become holomorphic and the other two become anti-holomorphic. That's almost clear because when R squared is rational, you can find an N and W such that this vanishes. In that case, we have more current. By current, I mean an operator with vanishing H bar or vanishing H. In that case, the current algebra is not just the U1 cross U1, but it's extended by this additional holomorphic operators. And in fact, one can show that the compact boson in that case is a rational CFT with respect to the extended chiral algebra. So we have a whole line of C equals to 1 CFT. Only when R squared is rational will you have a holomorphic capital U1 global symmetry. And only in those cases, the CFT is rational. So let's consider a particular case when R squared is an integer. It's a special case of it being rational. In that case, this is just a U1 level 2K WZW model. In this case, there's a holomorphic U1 current. And notice that holomorphic U1 current is always anomalous. This is like the chiral anomaly, the 2D version of the chiral anomaly. And if you use the formula right here for the general current, you'll see that this holomorphic U1 has an anomaly that has to be canceled by this classical Chern-Simons term in 2 plus 1D. And this is nothing but the U1 level 2K Chern-Simons term. The connection between the anomaly of this WZW model and the Chern-Simons term is the famous Chern-Simons WZW correspondence. Okay, so what do I have next? Okay, so now let me summarize the continuous anomaly for compact boson. So we discussed the free compact boson with the radius R, At any radius r, there's a U1 momentum and a U1 winding global symmetry. There's an exact T-duality exchanging R with 1 over R. At the same time, it exchanges the two U1 symmetries. At any radius R, there's a mixed hoof anomaly between the U1 momentum and the U1 winding. It's captured by a 2 plus 1D SPT given by an off-diagonal Chern-Simons term. If R squared is rational, then there's a holomorphic and an anti-holomorphic U1 symmetry. They are integer linear combinations of the momentum U1 and the winding U1. The anomaly for that holomorphic U1 is captured by a diagonal Chern-Simons term. Furthermore, when R squared is rational, the CFT is also rational. Okay, so that's the second part of the lecture. So I talk about the 1 plus 1D free boson. There's a U1 cross U1 anomaly. At this point, let me also make a comment that, again, sometimes people say anomalies have to be related or tied to the presence of fermions. But here we see that even in a 1 plus 1D free boson theory, there's already a non-trivial anomaly. Okay, so before I move to a more subtle discrete anomaly, is there any other question?
Can I ask a question?
Yeah.
Or maybe it's going to be related to what you're going to talk next. So you mentioned that in for the quantum mechanics case, there was this nice physics connection. Given the anomaly, I could make some predictions about the spectrum, about the degeneracy of the ground state. So this case that you just described, this U1 cross U1, okay, there is this anomaly, but is there some juicy physics consequence that you can extract?
Some dynamical constraints. I think, yeah, I thought about this question when I prepared the lecture. The thing is that I think all the flows from the 1 plus 1D free bosons are quite easy. But I can mention one thing. So, for example, you can deform this model by, say, cosine 2 phi. Right, so that breaks the U1 momentum symmetry down to Z2. But the Z2 subgroup of the momentum symmetry still has a mixed anomaly with the winding. So this flow preserves some anomaly. Therefore, the low energy phase cannot be trivially gapped. But that's obvious because if you deform by this operator, this potential has two vacua. So the low energy phase is a Z2 symmetry breaking phase. So that's one application. It's not that juicy, but it's at least a sanity check that this flow has a preserves an anomaly.
Okay. Well.
Let me see if I can make another comment, which I actually prepare for later lectures. Do I want to do it now? Maybe I can do it now since you asked. Another application. So later on, I will talk about discrete symmetries, discrete subgroup of these two U1s. And then those discrete subgroups appear from in the condensed matter literature. And they are important anomalies that condensed matter physicists are interested in. In fact, one of the work that got Holden to win the Nobel Prize are remotely related to the anomaly that I discussed. But in that spirit, let me just mention one thing from a condensed matter point of view. There are many ways to realize though. So the 1 plus 1D CFT emits various microscopic lattice realization. One of the most famous one is the 1 plus 1D XY model. You can think about it as a statistical model defined on a Euclidean two-dimensional lattice. This is something that people solved decades ago. And the action of the XY model is given by this, where less than of a factor of 2. Sorry. Let me fix that. Okay, so the action is given by this. There's some coefficient, and you have a phase, U1 phase at every site. And the interaction is given by the nearest neighbor interaction. This delta means that we're taking the difference of the phi here versus the phi at the nearby site. So this is just a standard XY model. And since only cosine of delta phi appear in the action, we have a very large, you can call it a gauge symmetry of this lattice model. You can identify your phi with the 2 pi times the space-time dependent integer at every point in your space-time. This is because I only have cosine of delta phi. So if I shift my phi by an independent integer at every site, it's not going to make a difference. Put differently, from the lattice point of view, you only see e to the I phi. There's no phi. It's unlike the continuum Lagrangian, where you have a derivative of phi explicitly appearing in your Lagrangian. Okay, and this has important consequences. And let me get to that. So on the lattice, we have a U1 momentum symmetry that just shifts phi by a constant. It's still there, but there's no U1 winding anymore. The U1 winding symmetry, the currents in the continuums are derivative of phi. But as I just commented, because on the lattice, we only have e to the I phi. So if you attempt to define delta mu phi as an operator, it's not gauge invariant. So this is a microscopic realization of the C equals to 1 CFT, but it only sees one U1, but not two. It kind of goes the opposite direction of what you were asking, because now I'm putting the CFT as the IR limit, and in the UV, we have this lattice model. In the IR, we have the emergent symmetry and the emergent anomaly. In the UV, we only have one symmetry and there's no anomaly.
You're trying to say that since we have this anomaly, we could not have hoped to find a lattice model where these two U1s would be explicitly realized, because then we would probably...
That's actually, that was the common belief. But then we wrote a paper earlier this year showing that's not true. There is actually a lattice model realizing the two U1 and the anomaly.
Okay.
Maybe I'll talk about that later. Here, the point I want to make is the following: is the Bkt transition. So if you take the XY model and you take the radius, the coefficient in front of the action, in front of the integral to be very large, then I can safely expand the cosine, and I get a quadratic term, and it's not hard to see that it's described by the continuum Lagrangian. So the phase diagram of the XY model looks like this. When the radius is very large, it's described by the continuum CFT. In the UV, I only have one U1 momentum, but in the low energy, I have an emergent winding symmetry, and together they have an anomaly. That's no contradiction. It's quite common that in the UV, you have less symmetry, you have no anomaly, but in the IR, you have more symmetry, and there's an emergent anomaly. But that also means, but the absence of anomaly in the UV of this particular XY model also means that the low energy can be gapped. And that's indeed the case for the XY model. If you take the radius to be sufficiently small, the phase is trivially gapped. And that's not a contradiction, because the XY model doesn't have any anomaly. And the reason for this transition, which is the famous Bkt transition, is that in the UV, we only have the U1 momentum symmetry. So when I flow to the vicinity of the C equals to 1 CFT fixed point, there's no reason for me to forbid the winding operator. So the winding operator will be generically generated. But when the radius is too small, my winding operator will be too light, and therefore it will destabilize this gapless phase. So this isn't quite the answer to your question, but it shows how the anomalies are compatible with all this with these RG flows. It's not a juicy application.
No, these are nice examples. Thank you.
Okay.
Very nice.
Okay. All right. So I'll come back to this probably tomorrow. I just wanted to give a preview. All right. So now, any other questions about this U1 cross U1 anomaly in 1+1D? It's really like the 2D counterpart part of the triangle anomaly in 4D, except that here it's not a triangle, but it's just this diagram. Okay, if there's no further question, let me go to the third lecture, the Z2 anomaly in 1+1D. So we have talked a lot about the U1 cross U1 anomaly in the previous lecture. But now let's move on to anomalies of discrete symmetries. Unlike quantum mechanics, anomalies in 1+1D are not characterized by projective representations, and they are more interesting in many ways. A complete and general treatment of discrete anomalies in 1+1D will be using the so-called topological defect lines. And there's a whole fusion category formalism to describe them. I will not follow that discussion. It's very powerful, very useful. It captures all the aspects of anomaly, but it will be too mathematical for first course, I think. Rather, what I will do is that I will just try to be pedestrian. If you hand me a Z2 symmetry, I'm just going to gauge it. I don't know anything about anomaly. I'm just going to gauge it bluntly. And I'll see when I run into a trouble. When I run into a trouble, that's a diagnosis of the anomaly. And for simplicity, I will just talk about bosonic 1+1D CFT. And I will focus on a unitary internal Z2 global symmetry. But many of the things I said can be generalized to more general discrete symmetry. So I will talk about this Z2 symmetry anomaly in 1+1D, and this is the outline. Okay. So first, to diagnose the anomaly, we have to discuss some general consequences of having a symmetry in 1+1D. So let this blue H be the Hilbert space of a 1+1D CFT quantized on a circle. I'll call this the untwisted sector. It's just a fancy name for the ordinary Hilbert space of local operator. That's what I say here. So by the operator state correspondence, states in this Hilbert space are in one-to-one correspondence with the local operators of your 1+1D CFT. If I have a Z2 global symmetry, then I can twist the boundary condition on this circle by a Z2 twist. So that's shown schematically here. I draw a line, meaning that I implement the Z2 twist at every time. And what that means, you can think of this as a Z2 branch cut. The branch cut is topological, so you can put it here or you can put it here, that doesn't matter. And what this branch cut means is that, for example, if you originally have a phi, originally you demand phi to be periodic up to integer 2 pi periodicity. But now with the twist, you allow some more general Z2 action. So let me write it differently. So here's a Z2 action. So as you travel around the circle, you don't go back to itself, but rather there can be a Z2 action of phi. The Z2 action can be flipping the sign of phi as typical in orbital, or it could be shifting phi by a certain amount. So this modifies the quantization and gives you a different Hilbert space. And I will call that a twisted sector, H sub TW. So we have H as the ordinary Hilbert space of states. They are in one-to-one correspondence with local operators. And then we have HTW, the twisted sector. They are in, if you do the operator state map, you see that they are in one-to-one correspondence with point operator living at the end of the Z2 branch cut. So they're not local operators. They're operators with strings attached. And it will be useful to think about that. So before things get too abstract, let's review a familiar example, the Ising CFT. The Ising CFT has a Z2 global symmetry. In fact, it's non-anomalous, as we will later see. The local primary operators of the Ising CFT is what we learned in the first class of CFT. There are three primary operators, the identity, the thermal operator, also known as the energy operator, whose conformal weights are 1/2, 1/2. And then the order operator, also known as the spin operator, whose conformal weight 1/16, 1/16. Let's first look at the first row. We can subdivide the untwisted sector Hilbert space into the Z2 even part and the Z2 odd part. The Z2 symmetry flips the sign of the spin operator. That's what we usually learn in CFT. Now we can be slightly more advanced and talk about the twisted sector. These are operators living at the end of the Z2 branch cut. One of them is the famous disorder operator, mu. It also has conformal weight 1/16 and 1/16. The others are the fermions. These have the weight 1/2, 0 and 0, 1/2. Importantly, these guys, they do not have integer spin. So they have half into spin. But that's fine. I think CFT is a bosonic CFT. So its twisted sector have half integral spin. But the local operators still have integer spin, and that's good enough. The fact that the twisted sector can have half integer spin is because they are attached to strings, so they might not be mutually local with other local operators. Anyways, this is the four sectors of operators in the Ising CFT. This row are the local operators. These rows are the non-local operators with strings attached.
Can I ask a question? So,
Yeah.
so here you are using, of course, we know everything about Ising CFT, but in general, you are using the fact that there is some lattice model, local lattice model, which gives rise to this Ising CFT. Otherwise, you wouldn't guess that. I mean, if you just given abstractly some CFT with some operators and some global symmetry, how do you know that this twisted sector should exist?
That's a great question. So if you hand me an abstract CFT, well, first of all, we have to ask if there's a symmetry. How do I know there's a symmetry of this abstract CFT? Okay, that I might be able to figure out, by looking at the OPE. Maybe there's some selection rule.
Yeah.
So I think you will grant me with the first row. So I have my set of local operators, and I know how symmetry acts on my local operators. If you give me enough information of the CFT, for example, if we are talking about a free boson CFT, then I know everything about it, and I can just go ahead and quantize the free theory on the circle with a symmetry twist, right? Just like what I'm trying to do here. And by doing that quantization, I can figure out what this twisted Hilbert space is. I don't have to guess, right? I have a Lagrangian. I know how symmetry acts on my fields. I just work it out. In fact, I will work it out in the later part of this section, the lecture. But you can ask a more general question, very much in line of the Bootstrap philosophy. You hand me this local CFT data with the symmetry action on the local operators. How do I extract the twisted sector data? In 1+1D, there's a simple way to do that. It's by modular covariance. So you can consider the torus partition function. You take this as time, and you put a symmetry line here. This data you do know, right? Because this is how the symmetry acts on your Hilbert space. And you grant me that data. So you can compute this partition function on the torus. And now you can do the S transformation to take it to this form. This is the data you were asking about. And that tells you about the twisted sector.
Okay.
So yeah, so that's the answer. So at least in 1+1D, given the local operator data and the way the symmetry acts on the local operators, you can extract the twisted sector, and you can even extract the anomaly.
Sounds good.
Yeah. Okay.
So this is just a duality.
I haven't talked about the duality yet. So in the Ising case, yes, gauging the Z2 symmetry will be related to the Kramers one-year duality. But so far, I didn't do any gauging. Z2 is a global symmetry. I just divide operators into different sectors. So there's no duality yet. But later on, I will mention it. Okay, so we talk about the twisted sector. Now we are going to try to gauge it. So in 1+1D, what does gauging mean? Gauging goes under the name as overfolding in 1+1D. Gauging a non-anomalous Z2 global symmetry in 1+1D CFT consists of two steps. And for those of you who are not familiar with overfold in 1+1D, I recommend reading the famous review by Ginsburg, and this is discussed in every textbook. Here, I'm just going to spell out the procedure, but I will not derive it or go through it carefully. But importantly, there are two steps. First, you keep only the Z2 even state in the untwisted sector. So the untwisted sectors are your space of local operators. Your plus means that I'm only keeping the Z2 even state. This is completely intuitive and natural, right? You gauge the Z2 symmetry, so you throw away all the Z2 odd guys. You keep the Z2 even guys. In quantum mechanics, that will be all you do, and you'll be done. But in 1+1D, that's not true. You cannot stop at step one. You have to do the second step, which is that you bring in the Z2 even states from the twisted sectors. The reason you cannot stop at step one is because if you only do step one, generally you won't be able to define the resulting CFT on a general Riemann surface. This is tied to the modular invariance. So gauging or overfolding really consists of two steps. You throw away operators, but you also promote some non-local operators into local ones. Now in the overflow theory, which I'll denote by T tilde, there's a new Z2 tilde symmetry. We start with the CFT T with a Z2 symmetry. We gauge it. Since we gauge this Z2, the Z2 is gone. But in the resulting theory, there's an emergent Z2 tilde symmetry. Usually goes under the name of quantum symmetry, overflow symmetry. I think it was first discussed by Vafa in the 80s. This new Z2 is defined the following way. So the new CFT has two sectors, the H plus and the H plus TW. The states in the untwisted sectors are Z2 tilde even, and the states in the twisted sectors are Z2 tilde odd. The important thing about this Z2 tilde, this quantum symmetry, is that you can then gauge this Z2 tilde in the orbital theory to go back to your original theory. So the important lesson is that orbital or gauging a discrete symmetry in 1+1D is invertible. You don't lose anything. You start with one thing, you get to the new theory. The new theory has an emergent symmetry that helps you to go back. And mathematically, it's just because gauging is a discrete Fourier transform. So you can always go back and forth. Again, before things get too abstract, let's do it in Ising.
Can I ask a question?
Yeah, go ahead.
Is it simple to see then that the Z2 odd states of the original theory are the twisted sector for the dual orbit or the dual Z2?
Right. Yeah, that's exactly what I will go over in this slide. Yeah.
Thanks.
Yeah. Okay. So I'm going to exactly discuss this point in the case of Ising, just to make things more explicit. So we start with Ising CFT. These are the four sectors. I put them in different colors. And now we gauge the Z2 of Ising. as was already alluded to, Ising CFT happen the Z2 orbifold of the Ising CFT happens to be the Ising itself. But more generally, that's not the case. For this particular case, it's true. But it's still useful to distinguish the two. So we get a new theory on the right. So what happens? What are the relation between them? So the Z2 even local operators stay where they are. The Z2 odd operator, they are projected out. They used to be local operators, but after Z2 gauging, they got demoted. They used to be local operators with no strings attached, but now they're in the twisted sector. And what are the strings attaching them now? Well, they start as Z2 odd local operator, and you gauge a Z2. After you gauge, you have some Z2 Wilson line. And the Z2 odd operators are now living at the end of the Z2 Wilson line. Just like you start with free fermion, you gauge the U1, then the electrons lives at the end of the Wilson line. So some local operators got demoted to non-local operator. Meanwhile, some non-local operator who used to have strings attached got promoted to local operators in the gauge theory. And then there are some really unfortunate non-local operators who still stay as non-local operators. So gauging 1 + 1D is really like a change of social classes. You don't kill anyone, but you demote some of the guys and you promote some other guys. Some people are lucky, they're always local operators. Some people are not lucky, they're always non-local operators. And others exchange their social status. Okay, and now comes the problem. And that's, okay, I'm almost running out of time, so I'll end with this slide, but let me just say what the problem is. So this is the procedure of orbifold in 1 + 1D. And if you're not familiar with it, yeah, you can go to Ginsparg's review for a very nice introduction of this procedure. But let's go over the procedure again. The first step, we keep only the Z2 even state and project out the Z2 odd. All right, that's no problem. We can always do that. But in the second step, we are promoting some non-local operators from the twisted sector so that they become local. But there's a potential danger in the second step. How do we know the operators that we liberate from the twisted sectors have integer Lorentz spins? If they do not have integer Lorentz spin, they don't qualify as local operators, and they cannot be liberated. In the Ising case, the operator in question is the disorder operator. The disorder operator has H1/16 and H_1/16. So it has integer Lorentz spin. It's a scalar, as a matter of fact. So there's no problem to promote the disorder operator to a local operator because it has integer spin. But is that always the case? Is it always the case that you can find some integer spin operators in your twisted sector so that you can promote them to local operators after gauging? The answer is no, and that's exactly related to anomaly. Okay, I'll stop here and I'll continue tomorrow with how to think about this anomaly. Yeah, thank you.
I'm a bit worried, Shu-Heng, because you have a lot of interesting stuff and you are very relaxed, but yeah, probably not going to be able to finish all of it. I'm a bit worried that we are going to miss out. We're going to miss out some of the interesting stuff that you have prepared.
I'm definitely able to cover the Z2 anomaly in the next lecture, and then I have some. Okay, I can then I have some more topics that I'm not sure if I want to talk about. So there's a bootstrap bounds on anomalies and anomalies, and then there's a discussion of anomalies on the lattice. So I kind of keep them as if I have time, I can go over them, and if I don't, it's up to you. I can speed up next time.
Maybe next time when for your next lecture, if you have to go over time, like for 10, 15 minutes, 15, 20 minutes, it's no problem. So
okay.
you
If
shouldn't be,
if you
feel
want me,
free.
okay. Okay, if you want me to
Well,
I
now
can
you kind of
continue.
already now we kind of already lost momentum because you already said okay,
Oh.
good. It would be a bit anticlimactic to continue, but tomorrow feel free to
Okay.
Since it's going to be the last lecture, you are allowed to be
All
more.
right. Okay.
So let's go on for questions. Maybe someone has questions.
I do have a basic question. So in regarding this example you made for the XY model, where in the lattice model there is no U1 winding symmetry,
right?
While in the continuum limit we have this emergent symmetry,
Right.
And well, okay, that's a kind of a general phenomenon that when you go to the continuum you might have some emergent symmetries.
Yes.
But then in the first lecture, maybe I misunderstood, but I thought you said that anomalies are rigid with respect to RG flows, and that they don't move continuously. But now here it seems like you have a model in the UV where there is no anomaly and a model in the IR in which...
Yeah, that's a good question. Yeah, so the rigidity comments actually go in one direction. So what do I mean by rigidity? The argument goes as follows. So in the UV, you have some symmetry. So let's say we have some UV system, and we have some IR system. We have a GUV, and we have a GIR. And two things can happen. So sometimes GIR is bigger than GUV because of emergent symmetries. Some other times GUV might be bigger than GIR because the symmetry in the UV might not act faithfully in the IR. For example, the IR phase can be trivially gapped, and then you don't have anything to act on. So both can happen. Now, if you are a UV person, you start analyzing the system in the UV, then you can turn on background fields associated with the UV symmetry. And if the symmetry has an anomaly, you can detect that anomaly by analyzing the partition function coupled to the UV background gauge field. And you can detect the anomalous gauge transformation here. In the case, but as a UV person, you don't have access to the IR stuff. Right? It doesn't make sense to turn on the IR background gauge field in the UV. It was not there. So the rigidity statement is that if you have some anomaly in the UV, those UV anomalies have to be preserved. And it doesn't make sense to start from the UV to turn on the IR background fields and talk about their anomalies. It's perfectly fine if in the IR you have some emergent symmetry and emergent anomaly. And once you go to the IR, you have access to those background fields, and then you can start talking about those anomalies. But the rigidity is about matching the UV anomalies with some anomalies or some other things, but with the degrees of freedom in the IR.
Okay.
So the argument really go one way.
Goes only one direction. Okay.
Yeah.
Can I ask again about this relation between the two Z2s? So okay, so in easing, this is all more or less clear. You can see it on the lattice, etc. But I did not quite understand if how do you see that this is general? So for instance, a necessary condition for the dual Z2 or whatever, the dual symmetry between twisted and untwisted is to be gaugeable so that you go back to the original theory is that the twisted sector is the old sector you threw away. And this, is there, for instance, a partition function proof of this fact in general that you get back the same dimensions? And also, did we prove that, so this is a necessary condition, but I don't know if it's sufficient. So could it have happened that you gauge this new Z2 and you go into something else, which is not the original theory, in which maybe the operators are the same, but I don't know, the OP coefficients are different. I mean, how do we prove that this is an evolution?
Yeah, this is a good question. So first of all, there's an ambiguity. Well, not for Z2, but generally there's an ambiguity in what we mean by gauging. Generally, when you gauge, you are always allowed to add local counter terms. For Z2, it's not so the case. It's not the case because the local counter term choice is very limited. But more generally, if you gauge Z2 cross Z2, you have to choose a local counter term, and then you can get different theories. But let me focus on Z2 and try to address your question. And the answer is yes. So there are many different ways to prove this statement completely from the CFT abstract or quantum field theory point of view. You can see it from at the level of the partition function. You can play with the torus partition function. From the torus partition function point of view, the overflow theory, written as this. And by following the definition of Z2 tilde, you can really check that various sectors go into each other as follows. So you can really work this out very explicitly by playing with the torus partition function. There's an even more general argument, which is this.
So this argument with the partition function would work in any CFT which has a Z2 subgroup, so it doesn't have to be the Ising model, or?
Yes, correct.
Okay.
Doesn't have to be Ising, just any CFT with a non-anomalous Z2.
Okay.
But wait, it's not in general true that you get an isomorphic theory.
It's not, no, oh, I'm not saying that you get an isomorphic theory. Sorry, I meant that how the sectors got permuted in this fashion.
But what you get after the gauging could be completely different.
Absolutely.
But then you would still have a Z2 to go back, right? If
Correct.
This would still be true.
Correct. Okay, maybe I misunderstood the question.
No. Yeah, I think Shu-Heng. Yeah. Thanks for the comment, but yeah, the question was this that you're answering. Thank you.
Okay. Yeah, generally this red sector is different from the green sector, and therefore when you do the gauging, it's not isomorphic to the original guy. Right. For Ising, it just so happens that this sector is isomorphic to that sector. So when you swap them, oh wait, it's the same. But generally, that's not the case. There's another formal way to say this. So the partition function of the gauge theory can be, there's some normalization, can be written as follows. So you take the partition function of the original theory, and you couple to a dynamical Z2 background field. So this H1 is just saying that it is some discrete Z2 gauge field. And this is gauging, right? So what does it mean by gauge? You just sum over all possible Z2 gauge field. It's a sum because it's a Z2 gauge field. Usually, if it's a U1, you path integrate the field. Okay, and then what is the Z2 tilde? Z2 tilde is the following. You can dress this so you can add such a term. This is the intersection pairing between the two one form on your Riemann surface. So you can turn it off, then we're just doing gauging. But then you can choose to add such a coupling, and then the partition function depends on A tilde. And this is actually the way that the Z2 tilde is defined. Now, why does this make it obvious that gauging twice take you back? It's because we can just then do the sum on the left-hand side. But then there's an identity about the intersection pairing that if you oops, sorry. That if you sum over A tilde, for example, then it will set A to be 0. It's an orthogonality condition.
Yeah, thanks. If I can ask one more thing, the last thing I promise is if
Yeah,
if
no
were
problem.
to,
Yeah, go ahead.
if you were to gauge something else, which is not like a bigger discrete group, say, then would you still have another? I don't know, if I gauge a Z3, is there another Z3 now? But there is still either twisted or untwisted. So is this involution still true?
That's a very interesting question. So the general statement is that if you gauge a finite group G, you get Holm G. Now, for abelian groups, this is isomorphic to that. Actually, I think there's a, let me try to write it in a more palatable way. Right, so how do you think about the emergent thing? There's actually a very intuitive way to think about it. You gauge a G symmetry. It's a finite group, so at the end of the day, you'll get some Wilson line of G. But the G Wilson lines are labeled by representation of G. And then they should be viewed as the quantum symmetry. If you gauge a Z2, what are the representations of Z2? There's a trivial representation, there's a sign representation. And the representation ring of Z2 is again Z2. So and that's the way to think about the quantum Z2. But interestingly, if you take G to be a non-abelian finite group, then the representation ring will not be a group. So what you get here is generally not a symmetry. And that's how this leads to the so-called non-invertible line. So there's a more general formalism dealing with these topological lines. It's not described by groups and their anomalies, but it's described by a more general fusion category. And the simplest example is to view them as the Wilson lines of some non-abelian finite group.
Okay,
and there's even a notion of gauging these non-invertible lines that will take you back. But that's certainly outside the scope of this lecture.
Okay, thank you.
Yeah. Thank you for the nice questions.
I'm waiting if there are any other questions.
Yeah, I actually have a question. So
Yeah, please.
going back to this example of forming the free boson, and you chose this cosine of 2 phi.
Right.
Is it a non-trivial example if it deforms, say, by cosine of 2 phi tilde, or?
By duality will be.
Yeah, okay, sorry.
Yeah.
Yeah, thanks.
No, but there is a non-trivial example where you add them both together.
Yeah, that's true. I think it's still a Z2 breaking phase, no?
Yeah, but it's less obvious.
It's less obvious, yeah. And there's also a case where you can do the following, right? You can add cosine phi and cosine 2 phi tilde. Or more general, actually, let me do it this way. Cosine phi tilde and cosine n phi. And I think that takes you to the Zn clock model. That's a very interesting flow.
And what can you say about this model using, you say you can say something interesting using the anomalies by this flow?
Well, for this particular one, no, because this guy completely breaks the winding symmetry. Yeah. So you have to, yeah, so as Zohar was saying, you can add both, maybe with a coefficient n. And then I think anomaly will enforce this. I think it's reasonable to expect the low energy phase is a ZN symmetry breaking phase.
Okay. Okay, very interesting discussions, but we still have time for more questions. If, people shouldn't hesitate.